Hello students, today I would like to introduce a new space which is called the LP spaces. So in order to define this space which is denoted by LP spaces, I consider let E be a measurable set. Let E be a measurable set of real numbers and define F to be the collection of all measurable extended real functions on E that are finite almost everywhere on E. So in order to define the capital P spaces, and this space consisting of first of all actually measurable functions. Okay, so for that we need a measurable set E which is a subset of real numbers, and F is the collection of all measurable extended real world functions defined on E that are almost everywhere on E. Okay, now in the collection of all measurable function F, I am going to define a relation on F. So before that, I would like to introduce when we say two functions in script F are said to be equivalent. So two functions F and G are said to be equivalent if f of x is equal to g of x almost everywhere on E, and it is denoted by f is equivalent to g. So two functions are equivalent means they are equal almost everywhere on E. What is the meaning of f of x equal to g of x almost everywhere on E means this, if you consider the set of all x such that f of x is not equal to g of x, then this set has the measure which will be equal to 0. So measure of all those points at which f of x not equal to g of x equal to 0. This is the meaning f of x equal to g of x almost everywhere on E. Okay, now I will define a relation on F. Now define a relation tilde on script F such that if you take any two elements in the script F is related to G if and only if F is equivalent to G. F is equivalent to G. F is equivalent to G means that is F is equal to G almost everywhere on E. So I take two elements F and G in script F. They are equivalent, they are related means they are equivalent to each other. Okay, then I can prove that clearly this relation will be an equivalence relation, because every function, if you take F in script F, then I can say that F will be always equal to F. Okay, so F will be equivalent to itself. Therefore, this relation will be F is related to F, therefore it is reflexive. Second one, if you take two elements F comma G in script F, then if F is related to G means F is equivalent to G, which can be implied G is equivalent to F, therefore G will be related to F. Right? And for the third one, this means symmetry. If f comma g comma h belongs to script F, and if f is related to g and g is related to some h, then f related to g implies f will be equivalent to g, and g related to h implies g will be equivalent to h. So which implies f of x is equal to g of x almost everywhere on E, and g of x is equal to h of x almost everywhere on E, right? So which together implies f of x will be equal to h of x almost everywhere on E, which implies F will be equivalent to H. That means F will be related to H. So transitivity will be also can be proved by using these two statements. So tilde is transitive. So that means the relation tilde F is related to G if and only if F is equivalent to G. That means F equal to G almost everywhere on E is an equivalence relation on F. What is this F? This is collection of all measurable functions defined on E. So which implies tilde is an equivalence relation on F. Okay. Now, you all know every equivalence relation on a set will partition that set into disjoint equivalence classes. So, in the same way, this tilde will, therefore, this tilde induces a partition of script F into disjoint collection of equivalence classes, and its equivalent classes are denoted by F restricted to E. Some equivalence symbol denotes equivalence. Okay, so this F will be, first we have a measurable set which is a subset of our real number R which is measurable. Okay, then you consider functions f1, f2, etc., f and g, h, etc. These are functions defined on E which are real valued, extended real valued functions. So these are functions from E to minus infinity to infinity, and these functions are measurable. Then you take all collection f which is equal to some f, g, h, etc. That means each function f is a mapping from E to minus infinity which is measurable. Okay, so this is our script f. Then you find out a relation tilde. Then you defined a relation tilde on script f. It is a relation from f to f such that f is related to g if and only if f is equivalent to g. Then it is an equivalence relation. Each will partition our f into equivalent classes. So the whole f can be considered as, suppose this is the collection f, then it may be split into equivalent classes, disjoint equivalent classes, right? And each equivalence classes is denoted by f restricted to tilde. Okay, and what is this? This is collection of functions f, g, etc. Ready? So what is the equivalent class of f? Equivalent class of f is nothing but set of all functions which are equivalent to f. So equivalent class of f, suppose f belongs to this collection, first equivalent class, then equivalent class of f is nothing but set of all functions g such that f is equivalent to g, or set of all functions g such that f of x equal to g of x, right? Okay. Now I will prove that each equivalent class of script f is a linear space. Now I prove that each equivalent class of f, that is denoted by f restricted to equivalence is a linear space. What is a linear space? Linear space means it is a vector space. Linear space over R. So to prove it is a linear space over R, we have to define vector addition and scalar multiplication on this set. So how will you define the vector addition? You know, this equivalent class consists of functions. So if you take f comma g belongs to equivalent class of f restricted to equivalence, then you will define vector addition is defined as f plus g of x is equal to function addition fx plus gx, and scalar multiplication is defined as some some alpha into f of x is equal to alpha into f of x, where alpha belongs to real number scalar. Alpha is in a scalar. Okay, so under this vector addition and scalar multiplication, which is a, you can verify all the axioms of vector space. Therefore, it is a linear space over R. Okay, which is a linear space over R. Now, what will be the zero element? What will be the zero element of this space? The identity element. The identity element of this space. Identity element of this space is equivalent class of functions which are vanish almost everywhere on E. That means set of all f such that f of x equal to 0 almost everywhere on E. So this kind of functions, equivalent class of this kind of functions will form the additive element for this collection. Okay, so which is a linear space over R. Okay, now we go to our record collection capital LP. So how can you define capital LP? So now consider the family capital LP of E. What is this means? Capital LP of E denote set of all equivalent classes F for which integral over E mod f raised to p is finite. So which means you consider a set of all functions in the equivalent class of f such that this f satisfies the condition integral over E, Lebesgue integral over E mod f raised to p is finite. It is finite means this integral exists. That means integral over E mod f raised to p exists. Right? It is finite means it is exists. That means it is integrable. That is mod f raised to p is Lebesgue integrable on E. Is Lebesgue integrable on E. So you consider capital LP of E as set of all functions which are p integrable on E. P integrable means its pth power is integrable. Okay, p integrable functions on E. So what is this? Since they are integrable functions, Lebesgue integrable function, it is also measurable function, right? Since it is a measurable function, it must be belongs to script f, right? So this collection is nothing but a subcollection of these equivalence classes, right? Since this equivalent classes is a linear space, I can say that capital LP of E will be a subspace of these equivalent classes. Okay? This is a subspace. Since it is a linear space, this is a subset, and I can prove that it is a subspace also. So I am going to prove that this capital LP of E is nothing but a subspace of this equivalent class. One for some equivalent class. So in order to prove capital LP of E is a subspace of our equivalent class f restricted to equivalence, we need to prove that it is also closed under the same vector addition and same scalar multiplication, right? Okay, so for that I consider two elements f comma g belongs to capital LP of E. So which implies f comma g belongs to capital LP of E means integral over E f mod f raised to p is finite and integral over E mod g raised to p is finite, right? We want to prove that it is closed under vector addition. That means f plus g belongs to LP of E. This is our claim. To prove f plus g belongs to LP of E, we need to prove that integral over E mod f plus g, that is integral over E mod f plus g raised to p is finite. This is we need to find out. Okay. So what will be this? So we consider integral over e mod f plus g raised to p. Okay. Since mod f plus g raised to p will be a real number, right? Since it is a real number, okay, by triangle inequality we have mod a plus b will be always less than or equal to mod a plus mod b, right? For any two real number. Then I can write this will be less than or equal to mod a plus or mod a plus mod a if mod a equal to maximum of mod a comma mod b, right? So if you replace any of these element by maximum of mod a mod b, this can be written mod a plus b will be less than or equal to 2 into maximum of mod a comma mod b, right? So using this technique I can write mod f plus g will be less than or equal to 2 into maximum of mod f comma mod g. So using this idea, integral over e mod f plus g raised to p will be less than or equal to integral over e 2 raised to p. Here we have the power p, so we have to apply this power to this right side of the inequality. So 2 raised to p maximum of, right, maximum of mod f raised to p comma mod g raised to p. Or that is actually which is equal to integral over e 2 raised to p into mod f raised to p plus mod g raised to p. So which is always less than or equal to integral of modulus will be less than or equal to modulus of integral s. This is less than or equal to 2 raised to p into integral over e mod e f raised to p plus integral over e mod g raised to p. Okay. So what is this? Which is finite since f belongs to LP of e. And what is g? Since g belongs to LP of e, it is also finite. So these two are finite sums. So their sum will be finite. 2 into some finite value will be finite. So the whole thing goes to less than finite. So what you get? F plus g is an element which is also a measurable function which belongs to LP of b because their pth integral is exist. Pth power of integral will exist. Okay, so you get f plus g is also belongs to LP of e, which implies vector addition is closed. Vector addition is closed. Or LP of e is closed under vector addition. Now, for the scalar multiplication, let alpha be any scalar and f belongs to LP of e. Okay, which implies integral over e mod f raised to p is finite. It is integrable. Okay. To prove vector addition is closed, we want alpha into f belongs to LP of e. We want alpha into f belongs to LP of e. So for that, integral over e mod alpha into f raised to p must be finite. So you consider integral over e mod alpha into f raised to p. So which is equal to, what will happen? Integral over e, this can be written mod alpha raised to p mod f raised to p, right? So mod alpha raised to p can be taken outside, integral over e mod f raised to p. And what is this? This is finite. So mod alpha raised to p will be a number. Since alpha is a fixed number, mod alpha raised to p will be a real number. Therefore some real number into a summable value, that means it will be finite. So you get alpha f is also a function belongs to LP of e. Therefore it is closed under scalar multiplication also. So since it is a subset of a vector space, we need only check they are which are closed under both vector addition and scalar multiplication. Therefore I can say that capital LP of e is a subspace. In particular, it is a vector space. In particular, it is also a vector space. So capital LP of e is a vector space for 1 less than or equal to p less than infinity. So this p is varying from 1 less than or equal to p less than infinity. Okay. By the definition, for 1 less than or equal to p less than infinity, we defined LP of E. Okay.